All right, guys, welcome back to 61C. Hey, yeah, can you all hear me? Okay, cool. So, yeah, one of the cool things about having two professors in your course is there's almost always a professor here in Berkeley, right? But somehow Dan and Brian are both so popular that they're both gone today. We're left with me. So I guess I'll start out by doing a quick review of what we covered last class. We looked over the stored program concept, right? So can anyone tell me what's the first step you have to do when you're trying to convert an assembly instruction into 32-bit MIPS? Yeah, back there. Yeah, so I don't know, I'd actually count that as the second step. The first thing you really have to do is you have to recognize what format it's in. So you check if it's an R-type, I-type, or a J-type instruction, and that tells you what fields you have to fill out. One of the fields you always have to fill out is the opcode. You just look that up in the green sheet. Then after that's taken care of, you go and fill in all the other fields. Let's hope this is not a catastrophic error. Perfect. Okay, yeah, so today we're going to be talking about a few interesting things that you have to do to make MIPS work really well. It's kind of like, I call this the cat and mouse lecture of MIPS, right? There's a lot of stuff that you kind of have to think really carefully about if you're an ISA designer, if you're designing your own instruction set. And the people who did MIPS really did a really great job on it. And today we're going to look at some of the decisions they made. So the first, this was the review basically. Yeah, so you just have to come up with all of those to get your instructions. The first problem we have to deal with is the I-format instruction problem. So the question is, how do you put a 32-bit number into your program, right? Like, yeah, a question back here? You need more volume, right? I think I'm just going to hold it, actually. This is much better, right? Okay, so the first question is, how do you store really big numbers in your program, right? So say you have a register, and you want to store a 32-bit number into your register. How do you do that? So it turns out that you can't do it with just one instruction because the instruction is 32 bits and your registers are 32, so there's no way you could possibly encode all that information into just one instruction. So can anyone think of one instruction that will already help us out with this problem? Yeah, well, I heard it from a few people. It's LUI, but we're getting ahead of ourselves. The most important instruction for this is the OR immediate instruction, because OR immediate is what allows us to combine two numbers, right? If we have 16 high bits and 16 low bits, and we do OR immediate, it will put two registers together and make one giant register that has all 32 bits set correctly. So yeah, so basically this is just a sacrifice we had to make, right? We had to add one more instruction to be able to put 32 bits in registers. So can anyone think of a reason why we might need 32-bit numbers in our MIPS programs? Yeah. Yeah, that's actually the most common use. So if you want to address the entire memory, you might need to store a pointer to part of your program or part of some data into a register, right? And then you can call JR to jump to that register. It will take you to that part of the program. You can do a load or store instruction, and it will load that memory into your register. That's the main use for it. Does anyone have any questions about why this is really important to be able to store 32-bit numbers into registers? Okay, yeah. So you'll actually need it a lot on your project. You'll need it to store addresses, as we just mentioned. And also, there's one part where you want to create a signed overflow, right? So you'll be needing a big number to create an overflow, right? This is one way to do it. So the solution is to create a new instruction. In addition to OR immediate, which I just mentioned, we'll have load up or immediate. So I'll just kind of explain how these two instructions work together to solve our problem. You'll be, whenever you're trying to store a 32-bit number into a register, you'll call two instructions. The first instruction will store the first half of your 32-bit value, and the second instruction stores the second half of it. So let's say you wanted to store 0x FFFFAAAA into one of your registers, what would the first instruction have as its immediate? Yeah, all Fs. And your second one would have all As, right? So your first instruction will be load upper immediate, and the immediate will be all Fs, and the second one will be or immediate with all As. So load upper immediate will just take those bits that you have in the immediate field and store them into the first 16 bits of the register. And then or immediate will take the logical or of each bit with that original register. And you end up having all of them in the same place. So any questions about that? Yeah. In the back, yeah. Yeah, you. Yeah, that's right. So one way to implement LUI with two instructions, so what he's saying is if you didn't have load upper immediate, you could still get by. You could just store your upper 16 bits into one register, shift it left by 16 bits, and then do your or immediate like I just mentioned. But because this is such a common operation, the MIPS designers decided to make a trade-off, have one more instruction, and now just be able to do a 32-bit immediate in just two instructions. Yeah, good question. Anything else? Yeah. Yeah, so the trouble with AND immediate is that it will actually clear the first, I'm not sure if it actually does this, but it should probably clear the first 16 bits, right? Because if you do an AND immediate, I don't know, do any of the TAs know? Brian, do you know if AND immediate clears the first 16 bits?
Well, we can say right off the bat that if the load upper immediate has filled the bottom 16 bits with zeros, 0 and anything is going to give us 0.
That's true. Yeah, so even if it didn't, that wouldn't work because like it would clear part of your well, that wouldn't be a problem because it's already all zeros, right? But yeah, the fact is or immediate works, and maybe and immediate will also work if it doesn't clear the first 16 bits, but I'm not 100% sure if that would work or not. Yeah, anything else? What's that? If you're doing add. Well, add would actually work. Add immediate would work. Are you saying there would be like some problem with negative numbers or something like that? A carry. Oh, yeah, so you'd have to start out with a register that's all zeros. So you'd start out with a 0 register, add that to your 16 bits, and then store it in, and then shift left. It would all work out, but you know, it would use two instructions. Yeah, anything else? Okay. Yeah. Yeah, so that's the reason why. Why do you have to do it? It's because your immediate is only 16 bits. If you had 32-bit immediates, you wouldn't have this problem, but there's no way you could fit 32-bit immediates into a set with only 32-bit instructions. So here's an example, kind of like what I mentioned. These are the exact instructions you'd use to store that number into register T0. Oh, right. So do you see that $AT right there? That's one of the things I don't think we've talked about yet. It has to do with register conventions. AT is a register that you never want to use when you're writing MIPS programs. It's only used by the assembler. And what the assembler uses it for is for implementing these things called pseudo instructions. So if you type that first instruction into your Mars assembler, it might actually work. So it might actually appear that it has an instruction that can put a 32-bit value into an immediate, but can anyone tell me why that's actually not exactly what's going on? Yeah. Yeah, so that's why it actually won't work, but the reason why it will appear like it's working in Mars is because of pseudo instructions. So I don't know, could you raise your hand if Dan has covered pseudo instructions in here already? Yeah, I don't think he has. Maybe? Yeah. Well, a pseudo instruction is just an instruction that the assembler separates into multiple instructions. So whenever the assembler sees an add immediate unsigned with a big immediate, it will actually create two separate instructions in the final MIPS code. And which register should it use as the temporary register? Well, it can't just use any old register, right? Let's say it used T3. And let's say the person writing the program was using T3 for something else. Now, the assembler just clobbered their value of T3. Well, I'm feeling more and more like Dan every day now. The MIPS assembler just clobbered T3, right? And now your program won't work. So we have this special register called AT, and only the assembler is allowed to use it. The assembler can at any time just clobber the value in it. The program shouldn't touch it at all. So yeah, it says at the bottom, wouldn't it be nice if the assembler would do this for us automatically? It actually does. So now use iFormat for. Oh, okay. So this is actually a new concept. So any remaining questions about the iFormat problem? Okay, so this is another thing we have to solve. So far we've looked at all different kinds of instructions, right? But they were all mostly R-type and a few I-type. We didn't look at instructions that actually changed the flow of program execution. So there are two major types. There's the conditional jump and the unconditional jump. The conditional jump is something that's checking if something is true, and if it's true, it's jumping. Kind of like at the beginning of a loop, right? It checks if it should execute the loop again. If it should, it jumps to the beginning of the loop. If not, it just goes on. The unconditional jump is like $J$RA, right? Or $JAL$RA, something like that. It just always takes that jump. But the reason I bring that up is because they're implemented in different ways. These that check between different values, like BNE, BQ, right? These check two values, so they need to take a few register fields as well. So they couldn't be J-format instructions where you have just an opcode and then an address. They have to be an opcode, then an RS, an RT, and an immediate. But what did we just say about immediates, right? They're not big enough to hold giant values. They can only hold 16-bit values. So how big is your address space in MIPS? Yeah, 32 bits. So how are you going to go through your whole 32-bit memory space with just 16 bits? There's really no way to fix that. So the only solution is to use something called PC relative addressing. These instructions that do a little bit more than just jumping, they don't jump to a specific place in your program. They jump to where you are plus or minus a certain offset. And this isn't really a huge problem, right? Because if we're checking whether something is true or not, we're really doing either an if-else or maybe a loop or something like that. And loops aren't really telling you to jump to the end of your memory address, of your memory space, right? They're just saying, like, do a few instructions, then maybe if this is true, jump back 5 instructions, right, for a 5-instruction loop. So it's really no big deal that you can't reach the entire address space. You're only looking for things nearby. So what it does is we have this program counter, right? I think Dan mentioned there are better names for it than a program counter. All it does is it just tells you where in your program you are. Normally, it just gets incremented by 4 each time you do an instruction, right? It just goes on to the next instruction. So in this case, instead of just jumping forward by 4, if the condition is met, or maybe if it's not met, it will actually jump by some other number. So it's PC plus 4, like usual, plus your immediate. So if your immediate was 10, it would jump forward. Well, okay, so if your immediate was 16, it would jump forward by 16, right? It could also be something negative. Let's actually, I hate getting ahead of myself, actually. We'll get to examples later. Yeah, so this is how far you can move, right? You can move 2 to the 15th bytes. So, 1 second, 2 to the 15th bytes. And that's enough. That's enough basically if you're inside your original file, right? That's enough for any if-else, any loop, anything like that. So, yeah, so here's a little trick we do. Instead of using normal byte addressing for these instructions, we're using word addressing, right? Because it kind of lets us get a little bit more range. Does everyone see why that is? It's kind of just a bit of a hack. Instead of jumping a number of bytes, we're jumping by a certain number of words. So it will multiply it by 4 and then add it to the program counter. So does that make sense to everyone? Yeah. So here's the branch calculation I was mentioning. It takes the immediate, multiplies it by 4, and if the condition is met, it adds it to PC plus 4. If not, it just does a usual PC plus 4. So I guess that's the end of our discussion on conditional branches, which usually use PC relative addressing. Looks like we have a question about that. Yeah.
On the previous question,
Right.
you could branch plus or minus to the 17 bytes.
Yeah, that's right.
I do know back to the 17. If you don't have the structure, it's signed.
What's that? Like, it's not what? Oh yeah, it's signed. So the branch instructions always sign extend their immediate. So you can just use like you can just use normal 2's complement numbers. It tells you how far back or forward to go. It's really neat. And this is actually really useful because say you have a do-while loop, right? Then your condition is at the end of your loop. So it might have to jump back to the beginning of the loop, and that's how it's usually implemented. You just put the condition at the end, and it might jump back. Yeah, other questions? I might not be able to see, so kind of like wave your hand up and down, right? Okay, cool. So here's an example of branching. We're trying to do a loop here. So we're going to just keep following this loop as long as the condition is true. And at the end of each iteration, we just jump back to the beginning of the loop. So how do we write this as an I-format instruction? First, we look up the opcode in the green sheet. Well, first of all, what's the format? It's an I-format instruction, right? So like, if we had to convert this into a 32-bit instruction, we would write out our little boxes, right, with 6 bits for the opcode, then 5 for each of the registers, then a 16-bit immediate. And then we write the opcode, which is 4. We get that from the green sheet. Put that in the first field, 6 bits, right? RS is 9 and RT is 0. That's just what those two registers translate to. Yeah, so over there they wrote them as 9 and 0, right? But that's just to make it a little easier. Usually you'd write them as T and as T registers. Yeah, so you just write those, and then you have to find the immediate. So what's the immediate, right? Can anyone tell me what the immediate should be? Yeah. What's that? 1. Well, you're trying to jump to the end, right? So you'd always go forward by 1 instruction anyway, so that brings to add U. That brings you to add U. And then you have to go forward 2 more instructions to get to the end. So that's actually 3, right? Yeah. Any questions? Yeah. Well, you're not going back, right? It's checking if it's equal, and then it's jumping down 3 to the end. So yeah, if you had your check at the end of the loop, like if it were a do while, then you'd have a -3, and it would still work out. Now over there, you don't have to write -3, right? You don't have to write 3. You just write end because it's jumping down. Yeah, but the assembler will calculate 3 for you, and it'll all work out. Yeah, questions back there? Yeah. 12? Well, that's just because of the trick we did, right? So over here we did immediate times 4, right? So we don't want to store those extra zeros at the end of our immediate, because if we did, we wouldn't be able to access as much of the memory. So we just say 3. It always is going to multiply it by 4 and put 2 zeros at the end. So we just use 3, and it still works out. Yeah. So this is what it works out to. We have our 4, then 9, 0, and 3. Yeah.
Why do you add immediate unsigned as opposed to just add immediate on the slide before?
Let's see. So the slide before. Yeah, so that's a good question, actually. The reason why we have the unsigned there is because presumably this is coming from C code, Like usually we write stuff in C, right? And then it becomes MIPS. So it turns out that whenever we write something in C and convert it to MIPS, we need to use only unsigned instructions. And you might actually like lose points on a test or have something horrible happen to you if you don't remember to do this. So the reason why we use unsigned is because unsigned in this context means that we're not checking for signed overflow. So does anyone know why we're not checking for signed overflow here? What's that? Yeah, it's actually not even faster, right? It's just what C does. But yeah, it's the right idea, right? It's what C does. In this case, C does the thing that takes the least amount of work. It's not necessarily faster, but it takes the least amount of work. It just doesn't check for overflow. If the programmer accidentally overflows his or her integers, too bad, right? It's just going to crash. So whenever you can, if you want to write code that has the exact same behavior as C in all cases, you have to use the unsigned instructions. Yeah, Gino?
I was just curious, if you didn't want to put a label and you just wanted to put a numerical value, would it allow you to do that?
Yeah, that all depends on the assembler, but usually it will work, yeah. Oh yeah, why might that be a bad idea though? Yeah, right. So like if you start adding more instructions into your loop, your whole thing is broken now, right? It just it'll think it should go to almost the end of the loop instead of the end of the loop, right? So yeah, there was one more hand back there. Yeah. The immediate is assigned value. Yeah, the immediate. You mean for the end, right? Yeah, that's assigned value, and that's just so that we can jump back if we need to. Wow. Okay. Yeah. One more. Right. Yeah, so that's up to the green sheet, right? In this case, the green sheet says it's times 4. We're going by words, so we just do what the green sheet says, right? That's what we do when we create hardware. Someone had to decide, and here the decision was made this way just because it's a little more efficient, but it could work either way. Someone just had to decide. Anything else? Okay, so we have a few questions here. Why does the value in branch field change? That's just what we mentioned before, right? If we move the code around, we might have to branch to a different location, right? So the label stays the same, but it's going to a different place. The second one is what do we do if the destination is greater than 2 to the 15th instructions away from the branch? Okay, that's a good one. Does anyone have an answer to that question first? Yeah, we'll use a different instruction altogether. Yeah, so there was one more question back there, right?
Yeah, so to go back to the immediate time store,
Yeah, so what they meant, I think, was to the 17th. Wait. Oh, no, it is 2 to the 15th, right? Because you can go positive or negative, so that would be 2 to the 16th instructions, right? So if you want to go more than 2 to the 15th, you have a problem.
no, right, but
Yeah.
because the assembler multiplied by 4, doesn't it then have to store in a separate register?
Yeah, but they're saying how many instructions, right? So if they were saying how many bytes, it would be like 2 to the 17th, but they're saying how many instructions, so you can't do more than 2 to the 15th instructions. Yeah. Okay, I guess I'll move on now. So I was told we had no administrivia, but I guess some stuff has come up now. This project is worth 15% of your project grade. Part 2 is, so this is like a doom and gloom about the second part of the project, right? I think it actually has something about self-modifying code, so I'll give you a few hints about that. There are several different things you can do in self-modifying code. First of all, could I just have a show of hands? How many of you guys have heard about the concept of self-modifying code before? Yeah. It's kind of related to the stored program concept that we looked at during the last lecture. The concept that like any line of your program is actually just a number, right? The point of self-modifying programs is that you can always just like read a line of your code, change it, and store it back. So a program could actually be editing itself. And there are many different cool things you could do with that. You could start, if you had an itype instruction, you could start subtracting from the immediate field, right? So say you're in the middle of a loop. Each time you go through the loop, the instruction will have a different value for its immediate field. Another thing you could do is you could, if you had R-type instructions, just add something to your R-type instruction, and it will actually change it could change from like being an add to a subtract or something, right? So in your code, in your project, you'll have to figure out what some self-modifying code is doing. Yeah, so another thing, a lot of people were asking how to contact the reader, right? Because sometimes you have like a little dispute about grading or something like that. We finally posted all the readers on the website, so that should solve some problems. Yeah, any questions, any quick questions about the project, by the way? Okay, yeah. I guess we'll just move on, actually. We're kind of low on time. So the J-format instructions are an entirely different format, right? So far we've looked at R-type and I-type instructions. The J-format instructions have just a little bit of opcode in the beginning, and then a giant thing with a bunch of immediates. We only need it for two different instructions, right? We need it for jump and JAL. So yeah, so we just have, sorry, I take that back. It has 6 bits for the opcode. The rest of it is all immediate. So the trouble with this scheme is that we want to be able to address our entire memory with these jump and JAL instructions, right? But we have a bit of a problem because we already used up 6 bits of our instruction for the opcode, so we need, let's see, 26, right? Yeah, we only have 26 bits left for our address. So we can't actually get to the entire memory space, but we can do a little better than 26, right? Can anyone think of a trick we can do real quickly to bring it up to 28, maybe? Like, so that we can address 2 to the 28th instructions instead of just 2 to the 26th? Yeah, we can do it by words, right? Just like we did for the other case. So instead of addressing the memory by bytes, we'll be using words. So yeah, that's just a little optimization, and yeah, and the last two bits will always be 0. So yeah, where do we get the other 4 bits? We get it from the program counter, right? So we're just going to use we're going to say that we're always jumping within the same block of memory that we're in right now. And that tends to work very often, right? Because most jumps aren't going to like an entirely different part of memory. They're just going, between code. Like usually the code is all stored kind of together, right? So it's just jumping around between the code. If your code isn't too long, this will be a complete solution. And once in a while, we might want to jump to some other location really far away, right? So then we can just use JR. We can use load upper immediate and or immediate, put the address into a register, and then jump to that. So, yeah, question? Okay, so basically all that's saying is that we have to have a 32-bit for our bit address, right? So we know the last 28 bits are just going to be whatever we specified, but we need the first 4 bits. And the way we get that is we just take them from the program counter. And the program counter has the address that we're at right now. So it will just go to the address it will go to an address that's nearby. Does that kind of make sense? Yeah, so it's so basically all it's saying is it's not going to randomly jump to the beginning of your memory space. It will just go to wherever it is right now, but but jump around however it has to. I think I see one more question back there, right? Okay. So here's a summary. If we have our, if we called, let's see, so, oh yeah, so just a note about your green sheet, that symbol there means concatenation. So if you have commas, it just means that you're putting those bits together. So if it says like, if you had like some instructions on how to generate 4 bits, then 26 bits, then 2 bits, and you put them all together with commas, it just means put it all into one 32-bit value. Yeah, so here's an example where we tried to call, let's see. So we're already at an instruction that starts with 1010 for its address, and then we tried to jump to 1111, then a bunch of ones. What it does is it just goes to the existing address, first 4 bits, then all the ones, and then the last 2 bits are just 0 because it's supposed to be word aligned. Does that kind of, does that work for everyone? Okay. So now we have our peer instruction question. Sir, can we have some assistance with the peer instruction question?
Well, you want to read what it is?
Yeah. So for A and B, when combining 2 C files into one executable, recall we can compile them independently and merge them together. So which of these are true and which of these are false? Jump instructions don't require any changes, and branch instructions don't require any changes. True or false? So you guys can first try to work on it independently, then we'll see what we got, and then we'll do the whole peer instruction deal, right? Uh-oh. I think it's working. Okay, we'll have 20 more seconds. We'll have 20 more seconds now.
Oh, sorry about that, folks.
Well, it's not working. The iClickers aren't working. Sir, what shall we do about this?
We're going to let it roll off our back.
Okay. Yeah, so I guess this one just won't count for points then, but please try to answer them.
Yeah.
So yeah, this is somewhat undemocratic, I must say, but we're going to just look at the results from the people who have the iClick, whatever kind of special clicker it is. So yeah. What? Oh. Oh no, we're getting. Oh. People are gaming the system. Oh no. This is like the 2000 elections all over. Well, okay, Bush wins. Yeah, so, yeah, looks like a bunch of you said B. So let's take a look at the question. Oh, right, so now let's discuss among ourselves for like 1 minute. I guess this kind of already counted as peer instruction, right? Like, you guys didn't talk to each other, but you kind of did through the thing. Okay.
Scratching my machine.
Okay, yeah, so I guess we'll bring it back in now and look over this question. Yeah, so everyone please, let's get ready to discuss this. All right, so first of all, I have one other question, like a sub-question. Would it be a good idea to call branches to something in a different file? Like, let's say you have two MIPS files, you have labels in one file and one in another. Like, would it be good to say BEQ and then have your label be something in a different file? Like, does anyone have a reason why that would or wouldn't be a good idea? Yeah. Yeah, that's right. So separate files don't have any specific relation in how they're arranged, right? So it could be like this one's before the other or backwards, right? So if you tried to jump to a label in another file, there would be no way that the assembler could be able to tell what that offset should be. It could change depending on where it puts the other programs. So it turns out that branch instructions can only be within one file, and so they don't require any changes when you're when you're moving things around and combining programs. So that one's true. But number one is false because, like I just said, if you're putting two programs together, you can put them in any order, right? And you can rearrange them however you like. So depending on how you arrange them, you'll need to jump to a different address. So does anyone have any questions about that? Yeah. Yeah, so header files are for C, and the compiler will take care of all that before the assembler is called. But yeah, the assembler actually has its own system for handling this, and it's kind of related to the system of header files. It will have a separate file. Well, it'll have something called a relocation table where it stores all those addresses, and then there's a linker that rearranges everything. But that's for a different lecture. So. I'm not going to step on Dan's toes by giving all that away right now. Yeah, another question in the back? Well, no, it'll still be a bunch of different MIPS files, but the header file issue, like the header will end up in the file that's compiled, but the other files won't. It's kind of complicated. That's not really for this lecture. There's going to be a whole lecture just on. Hey, I haven't said in conclusion yet, guys. Yeah, so this is like something for a different lecture. I'm not really going to go into that much detail right now. Yeah, I guess I'll just keep going ahead. Yeah, so now I'm about to say in conclusion, but I still have a few more moments in the sun, right? So. 32 bits representing a single instruction. So these are all the formats you have. They're all on the green sheet. So if you have that with you, you're safe. You can always just look up what it's supposed to be if you forget it. The opcode is always 6 bits. Registers are always 5, and the immediate is 16. But for jump, the target address is 26 bits. So branches use PC relative addressing. They just go to like +10 or -10. They don't go to a specific address, unlike jump and JAL. And disassembly. Right, so disassembly is when you have a bunch of 32-bit numbers and you're trying to go back to MIPS, right? So computers actually come with a program called a disassembler, where you can take like an executable file and convert it back into a MIPS file. So that's going to be covered next time. And yeah, the first thing you do if you're trying to go from a 32-bit number to an assembly instruction is you find the opcode, then you find the type of the format of the instruction, then you find all the other fields, and then you get the actual instruction in MIPS form. Yeah, so I guess that's all we have for today. I'll stick around for another 10 minutes in case you have more questions, and yeah, have a nice weekend.